Welcome to Trigonometry, Lesson 12.5. We are going to learn about trig identities. So trig identities are a relationship between trig ratios, and they're very important as far as trigonometry. The identities are the squares of the sine and cosine of an angle. So I'll say that again. The trig ratios we're going to study, the identities, are the squares of the sine and cosine of an angle. Instead of using sine x, which would also be something like sine 30 or sine 45, instead of including that expression and just squaring it, and this would apply also to like cosine x or tan x squared, we use the expression sine squared x and cosine squared x. So you need to have this in your notes right away. You will not do the form where you're doing sine 30 and then squaring it. And you'll see that as we're working along in the problems. Here's an example. If x equals 9 degrees, then in the format that we want to use, we would say cosine squared x. So it'd be cosine 9 degrees and I know this is going to be strange, squared, cosine 9 degrees squared, which will equal 0.98772. I'm sorry, which is 0.98772, and this should say squared here. So let me fix that. Which is 0.9755. So once again, I know this is strange, but we write the expression cosine squared x, but when we actually perform it, it'll be cosine 9 squared. In my calculator, I go 9 degrees cosine, and then I push the squared button. So what you want to do with your calculator is figure out what order you'll use on your calculator to get this answer, 0.9755. So once again, I take the 9 squared, hit the 9 degrees, hit the cosine button, and then multiply by 9 degrees cosine again. So the first time that I did this, 9 degrees cosine, I ended up with 0.9877. When I did it again, that's the number that you will square. Okay? So if you go the other way around, where you're doing cosine 9 degrees and then you square that whole expression, that would be cosine 81 degrees, and that gives you the wrong answer. So try them both ways so that you get these answers, and then in your notes put down what you do not want to do. And I'm sorry I kind of flubbed that up, but we'll be working these in class, and prayerfully after a few you'll get what I'm saying. So here's an example in example 1, and we're going to determine sine squared x, cosine squared x, and sine squared x plus cosine squared x for each value of x. So we have for a, x equals 30. So let's go ahead and work this out, and I'm working it out the long way, and I'm using decimals. In your book they use fractions. If I can use a decimal instead of a fraction, I do. So it's up to you how you want to do this, but we already know that sine 30 was 1/2 or 0.5. So sine squared 30 would be the same as saying sine 30 times sine 30. which would be 0.5 times 0.5, which equals 0.25, which, as far as I'm concerned, that's a great answer. But for your textbook's intent, they are using fractions, so I converted to 1/4. So here you can see that they've taken, instead of 0.5 squared, they've done 1/2 squared. Now cosine squared 30 would be the same thing. Cosine 30, which is 0.866, times itself again, 0.866, which is 0.75, which equals 3/4. And you can see that there in the box. Now the ultimate of this, they want to take these two expressions, the sine squared x plus cosine squared x, and add them together. And if you've done this correct, they will be the answer 1, or very close to the answer 1. So close that it would be approximately 1. So we have our 1/4 and our 3/4, and we add them together and they equal 1. So let's look at B. This is sine 45, and you may recognize already that sine 45 is 1/2, or 0.5, which was one of the expressions I told you should probably memorize. Well, sine 45 is 0.7071, I believe. I just put 707 to be able to fit it on the slide. But if we multiply that number by itself, it equals 0.5, which is 1/2. So we have our answer here, 1/2. And guess what? The cosine and the sine are the same here. And that's because, remember back to your 45, 45, 90 right triangle, you have two 45-degree angles. So sine and cosine are the same in that triangle. And 1/2 plus 1/2 would equal 1. So your sine squared 45 plus cosine squared 45 equal 1. Now C is just a little bit different. It's not one of the standard angles that we use for trig, so you'll have decimals and you won't be using fractions for this one. So sine squared 75 is sine 75 times itself. Sine 75 is 0.9659 approximately times itself, and that's 0.9330. So you can see this on the in the table. Cosine squared 75, cosine 75 is 0.2588. Squared would be 0.0670, and here it is in the table. And if we add those together, they equal 1. So we've just proved that sine squared x, some unknown angle, plus cosine squared x equals 1 for any value of x. An equation that is true for all values that equal 1 of a variable is called an identity. We've studied identities before at the beginning of Algebra 1 and at the beginning of geometry also, and that leads us to Theorem 12.5.1, which is the Pythagorean identity. So we've used a theorem before, now we have an identity for trigonometry, and it says basically that for any angle x, sine squared x plus cosine squared x equals 1. So take a look, and we have our standard triangle. In this case, we've taken angle A and we've named it x. So when it says sine x, they're referring to the overall formula. This is your formula. But in this case, it's also angle A. Just so you relate that to the drawing. So we know that sine from our trig ratios. Sine x would be opposite over hypotenuse, A over C. And cosine x would be adjacent over hypotenuse, which is b over c. So what they've done is replaced the trig ratios with they've entered the trig ratios into this equation. Instead of just saying sine 2x, we can now say essentially a over c, or cosine x would be b over c equals 1. Now let's go ahead and take these two expressions and eliminate the denominators by multiplying by c, and we end up with an equation that says a equals c sine x plus b equals c cosine x. So these are the two expressions that are above here, just multiplied by c and eliminating the denominator. What we do with this expression now, these two equations, is we substitute them into the p-theorem. So the p-theorem is the same as it's always been, a squared plus b squared equals c squared. So a squared will equal, and let me get my pen and make this a little clearer. So a equals c sine x. There it is right there. So c sine x squared, this whole expression squared. b equals c cosine x, and we will square it, and they both added together equal the hypotenuse squared. Now we need to remember at this step that the square root of sine x equals sine 2x. So we go ahead and make that conversion that I showed in the previous slide. We actually write it sine squared x instead of sine x squared. So that's all we're doing, is converting this to the proper format and adding our square to the c. So take a look at that carefully. C times c will be c squared. Sine times sine will be sine squared, and we just drop the x down. And we do the same thing with this expression. So we've rewritten the expression, and guess what we have? We have our trig identity, sine squared x plus cosine squared x equals 1. So you just derived these two sets of equations to prove the identity. Now there are other forms of trig identities that are created from just subtracting from the original trig identity. So here's your original trig identity right here. Sine squared x plus cosine squared x equals 1. If we subtract cosine squared x from both sides, we can convert this property, and you see that is now in a new form. It's sine squared x equals 1 minus cosine squared x. And if we take the same original identity and subtract sine squared x from both sides, we end up with cosine squared x equals 1 sine squared x. So on the last slide, this is your first identity. This is identity 2, and this is identity 3. They're all the same, but they're used for different purposes and different information that you might have. So in proving identities, you can simplify the more complicated side of the identity or transform both sides into the same expression. And let's see what that looks like. And I'm sorry if this is a little difficult to read. I took it straight from our text. So we're going to use triangle ABC to prove that tan angle x equals sine x divided by cosine x. let's take this sine x divided by cosine x and simplify it. And this is what they were talking about in the last slide. So we begin with the more complex side of the equation and substitute simpler expressions for sine x and cosine x. So we know that sine x is opposite over hypotenuse, a over c. So let's substitute that. So sine x becomes a over c, and cosine x becomes b over c. We can now cross this part out because it equals this expression. Now, when you're dividing fractions by fractions, remember that a over c, if it's divided by b over c, is AC is being divided by, it has to be multiplied by its reciprocal. So that's a blast to the past. Back when you first began to divide fractions. So we'll multiply by the reciprocal. And the reciprocal means the second fraction will be flipped, and we can now eliminate these and sorry about that. That's a little glimpse of what happens to my program sometimes when I'm writing for you. So we've cross-canceled. Oops, and I now need to reset all of my parameters here. And we end up with a over c divided by b over c equaling a over and I just noted this. That was a b. Sorry I wrote a d. Equals a over b. So once again, let me just restate this, and I'll actually make a little correction here. So we had AC being divided by BC. We will multiply by the reciprocal, and that'll be AC times CB. And if we cross-cancel both C's, we end up with AB. And AB equals tan x. So tan x equals AB. Let's take a look at this. Tan is, remember your TOA, opposite over adjacent. So did we prove that? Well, opposite is A, and B is over adjacent. Yes, we did. This is something you'll want to have on your notes. This table is similar to a table I gave you at the beginning of chapter 12, so you might want to add these on the same page. Now, each one of our original trig ratios, which was sine, cosine, and tan, has a reciprocal ratio. And those reciprocal ratios are called secant, cosecant, and cotangent. Secant is the reciprocal of cosine, cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. So let's take a look at what they show you in this table. So here we have secant A, and secant A equals 1 over cosine A, which is hypotenuse over adjacent, which is C over B. So if I ask you to find secant A, you will be finding the hypotenuse, C, right here, over the adjacent, which is B. And if we go for cosecant A, That is the reciprocal 1 over sine A, which would be hypotenuse over opposite. Now remember, sine A is opposite over hypotenuse, so you're basically flipping that. So instead of A over C, you'll have C over A. And cotan, instead of being like tan, which is A over B, will be B over A. So cotan angle A, it's still the same angle, will be adjacent over opposite. So you want to write these down next to your other ratios, and these are actually the 6 most important trig ratios that we'll be using. So we have homework. It's all on page 606, numbers 1 through 9. And we're going to determine, and these are problems 1 through 4. I will do problem 1 here to just show you what they want. And it says determine sine squared x, cosine squared x, and sine squared x plus cosine squared x for each value. So this should sound familiar. We actually already did these problems. So sine squared x was 0.7071 squared, which is approximately 0.499, or I'm going to say 0.5, so it's 1/2. Cosine x squared, remember sine and cosine are reciprocals of each other. I'm sorry, equal to each other, so it will also be 1/2. And if we add 1/2 plus 1/2, we will have 1. Now if you go to do one of these problems and it's one of the decimal problems and it doesn't come out quite right, that means that you've rounded incorrectly. Just go ahead and take a look at your unrounded decimals to make sure you round them so they'll add to 1. Homework problem 5. The 3 answers for this problem are on the video, and the first identity, theorem 12.5.1 on page 603, is the first answer. The other 2 answers are on the next page, page 604. And your last 3 problems 7 through 9, all use this same triangle, our standard triangle. And number 8 says to use triangle ABC to show that each statement is true for acute angle A, and then its complement, angle B. So, tan angle A equals opposite over adjacent, which is A over B, and cotan angle B is adjacent over opposite, which is B over A. So, tan A equals cotan B, which is your answer. Now, how do you know that this is true? If you want to, you could substitute a degree measure there. You could say tan 30. If this was tan 30, then cotan B would be 60, and you can work it out and you will see that they are equal together. So number 7 and number 9 will be similar. You'll be using your ratios for both your tan and your cotan, and if you have any difficulties, be sure to contact me. I know this is very different, this is very new. We will be reviewing this in class and also doing some practice problems. Talk to you again soon.